I am S. Amirtharaj, Assistant Professor, EEE Department, Amet University. Today, I am going to deliver the topic on three-phase induction motor and their performance. So, our topic today, three-phase induction motor. The three-phase induction motor, nowadays 99% of application we are using three-phase induction motors. Our industries are tired to prepare to meet this demand. That now we will start our construction. The construction point of view, our three-phase induction motor, the two major parts of the three-phase induction motor, number one stator, number two rotor. So, we should be able to know how to construct our three-phase induction motor. So, first one, stator construction. The stator construction is common for induction motor, synchronous motor and single phase induction motor also. So, which is the outer frame for your three phase induction motor, the stator is a outer frame like this, and the slots are provided inner side of the stator like this. The slots are like this. This is known as slots. This is known as slots. Now, this is not a single piece, which is made up of number of stampings. Number of stampings. Each one is a stampings. Number of stampings are bunched together to make a laminated iron core. That is, this core is made up of the number of stampings, and the three phase windings is provided in the slots. And suppose if our total number of slots is 24 slots, 36 slots, take like this. If you want to construct 4-pole machine, so divide 4, that is 9 slots per pole. Again I am going to construct 3-phase induction motor. Again 9 divided by 3, that is 3 slots. The 3 slots are allotted per phase per pole. So, the 3-phase winding is placed in the inner periphery of the stator. So, the slots are in the inside, and also the windings are facing inside. So, the windings are laminated to reduce the eddy current losses. Anyway, this is the major points regarding our stator construction. Now, the next one is rotor construction. The rotor is a middle part, that is rotating part. The stationary part is known as stator, the rotating part is known as rotor. So, the rotor is placed in middle, which is going to rotate, So, the rotor, which is having two types of rotors. Number one, squirrel cage rotor. Number 2, face wound rotor. Number 2, face wound rotor or slip ring rotor. Face wound or slip ring. So, we have two kind of rotors, squirrel cage rotor. The next one, rotor construction. Rotor is nothing but a rotating part of a three-phase induction motor. So, the stationary part is stator, the rotating part is rotor. For your rotor, we have two kind of constructions. Number one, squirrel cage construction. Number 2, face wound or slip ring. According to this rotor construction, our 3-phase induction motor is divided into 2 types. Number 1, squirrel cage induction motor. Number 2, slip ring induction motor. For your squirrel cage and slip ring, for your squirrel cage induction motor, which is like a DC shunt motor, which is having moderate starting torque. For your slip ring induction motor, which is like a DC series motor, which is having high starting torque, or otherwise we can increase the starting torque by adding some external resistance. Okay. Now, I am going to draw the simple diagram to represent what is squirrel cage induction motor and what is slip ring induction motor. So, for your squirrel cage induction motor, squirrel cage rotor is having the structure is like this, there is cylindrical structure, and the slots are cutted in the outer periphery of the rotor like this. The slots are cutted in the outer periphery. The slots is nothing but which is the space which is ready to receive the windings. So, the slots are like this and the shaft is like this. Now, the very important difference between the squirrel cage induction motor and the slip ring induction motor is, for your squirrel cage induction motor is not having windings. The rotor copper bars, that is nothing but farmer wound copper bars. Copper bars are placed in the slots and mechanically welded, and the both end of the slots, both end of the copper bars are shorted themselves with the help of the end rings, that is both side one end ring is there and tighten themselves. So, all the copper bars, that is all the windings rotor bars, that is rotor conductors are shorted themselves. So, which is looking like a squirrel cage, that is why it is called squirrel cage induction motor. The main drawback of this construction is we cannot add any external resistance, which is rigid in construction, the compact in size. But for your slip ring induction motor, the small difference, instead of copper bars, here 3-phase windings is placed, but construction is like this, but instead of this is here some end ring is placed. For your slip ring induction motor, instead of copper bars, the winding is provided, the 3-phase winding is provided, but for your 3-phase winding, the one end of the winding is joined together and another end is left free like this. One end of the winding is joined together, that is neutral, another end is left free, and the rotor is like this, the internal structure. Now, here some slip ring is placed, provided, and the another end of the winding is N set slip rings like this, N set slip rings. Now, the another end of the slip rings is connected to some rheostat. So, the construction is like this, but here we cannot add any external resistance, we cannot change our starting torque, but here the another end is connected to slip rings, the slip rings also rotating with the rotor, and another end is connected to the rheostat, 3-phase rheostat. Now, by changing this rheostat, we can change the rotor resistance. So, we can add some external resistance in the rotor circuit for your slip ring induction motor, but which is not possible for your squirrel cage induction motor. So, this is the major points regarding our construction. Now, the next one is principle of operation. The next question, why it is rotating? If the supply is given, why the rotor will rotate? That is our main question. So, the next question will be arises, why does our rotor will rotate? Why does rotor rotate? So, some force will develop to rotate our rotor. That the force is needed, if the rotating force is developed, then only our rotor is going to rotate. So, next question is, why does the rotor will rotate? That is our principle of operation. What is our principle? Our principle is nothing but mutual induction. Mutual induction. That is why this motor is called induction motor. What is mutual induction? So, now the supply is given to our stator, our rotor is going to rotate. So, supply is given to the stator. So, the stator is an outer frame. We are going to conduct the supply in the stator, that is 3-phase supply. But rotor is in middle in the air gap. The rotor is going to rotate. That is known as induction, under the principle of induction. That is why this is called induction motor. How it is possible? Now, if the supply is given to our stator, which produce rotating magnetic field, that is, on rotating magnetic field we can prove this concept. The rotating magnetic field will develop in the air gap which rotate in the clockwise direction. So, here if the 3-phase supply is given like this, the rotating magnetic field will develop like this and rotate in the clockwise direction, at constant speed, that is known as synchronous speed. And what speed? It is synchronous speed. We can find the synchronous speed like this, depend upon the frequency and the number of poles. Ns is equal to 120 F by P. Now, if the 3-phase supply is given which produce on rotating magnetic field in the air gap, the stator flux is rotating in the air gap in the clockwise direction. Our rotor is stationary. This is our rotor. The rotor is stationary. The rotor also having conductors, we know, already we see the construction, outer frame which is having the conductors. Now, our magnetic field is rotating in the air gap which touches the rotor conductors, that is, sweep passed over the surface, which touches the rotor conductors. Now, due to this, one EMF induced in your rotor conductors. Now, the supply is given to the stator, one rotating magnetic field will develop, now which sweep passed over the rotor conductors, now an EMF induced for your rotor conductors. Now, our rotor conductors are shorted themselves, we know, we already see the construction. If the circuit is closed, it will produce one current. Again here one current will develop. Due to this current, one flux will develop. The flux will set up in the rotor conductors. So, now the first flux will flows like this. Now, one more flux set up in the rotor conductors according to the Lenz's law, such as to oppose the cause producing it. That means this flux will oppose the original flux. That means which rotate like this, okay, in the opposite direction. Now, the originality of the main flux, that is stator flux, the stator flux, now we push the stator flux, that is why the stator flux is bent like this. That is why the stator flux now tries to comes to the original position. That is why one force will develop in the clockwise direction. Now, rotating magnetic field also clockwise direction, we know the speed, synchronous speed. Now, our force will develop also in the clockwise direction in the air gap. Now, the rotor starts rotate in the same direction of the stator flux. Now, the stator flux speed is ns. Now, the rotor also starts rotating in the clockwise direction, that is taken as n, that is rotor speed. The rotor speed is n. Rotor is now rotating, starts rotating, and this is stator flux is rotating the air gap, not stator is rotating, stator flux is rotating in the air gap. Now, what is the speed of the rotor speed? The rotor starts rotate after the revolving flux. That is why the rotor rotates just behind the stator flux. Some difference will exist in between stator flux and rotor, that is known as slip speed. The slip speed is nothing but ns minus n. Some difference in speed will exist in between stator and rotor, that is known as slip speed. Now, we can derive the formula for percentage of slip. Percentage of slip is nothing but ns minus n divided by ns into 100, that is percentage of slip. Now, we should understand one point. When the supply is given which produces rotating magnetic field under this principle of mutual induction, an EMF induced for your rotor at standstill. Now, the rotor is not rotating. At standstill condition, the frequency of the EMF induced in your rotor conductor is same as the supply frequency. So, the frequency of the EMF at starting is same as the supply frequency. Now, after rotation, what is happened? After rotation. After rotation, the frequency of the rotor current, that is taken as f dash, frequency of the rotor current f dash. F dash is equal to slip times supply frequency, slip times supply frequency. So, the f dash is equal to S into f. Now, what is happen? During rotation, our frequency will changes. Because of the frequency changes, our performance equation also going to change due to this frequency changes. So, now I am going to derive the torque equation. What is torque? So, I am to understand now one torque will develop, that is one force will develop. Due to this force, our rotor is going to rotate in the clockwise direction. Now, the question will be arises. The rotor can catch the synchronous speed. It is possible or not? If the rotor catches the stator flux, what will happen? If ns equal to n, what will happen? If ns equal to n, what will happen? Already I told our rotor always rotates less than the synchronous speed. If ns equal to n, if the rotor catches the synchronous speed, that means our rotor and stator flux rotating the same speed. The no flux cut by the conductor. Now, the EMF induced in the rotor conductor only possible to rotate our rotor. If our rotor flux and stator flux is rotating at the same speed, is not possible the flux cut by the conductor. That means not possible for EMF induced for your rotor conductors, not possible for the production of current. So, not possible for the production of force. That is why our rotor is not possible to rotate if our rotor and stator flux rotate at the same speed. That is why there is never rotor catches the synchronous speed of the stator flux. Okay. Now, Now, the next one we are going to derive the torque equation. What is the torque? The torque is nothing but twisting moment about an axis. Torque is nothing but the twisting moment about an axis. So, already we studied our torque equation of DC motor. Always we are studying our 3-phase induction motor by comparing our DC shunt motor, because the performance is nearly matches our DC shunt motor, because our DC shunt motor is moderate starting torque, our squirrel cage induction motor also moderate starting torque. Now, so our DC motor, the torque equation is familiar. Torque is directly proportional to phi into Ia. What is phi? Phi is nothing but the flux per pole, and Ia is nothing but the armature current. Because our DC motor armature is rotating, field is stationary. So, this is the we are starting our we are going to derive the torque equation from our DC motor. DC motor torque equation is taken as base for our induction motor torque. Now, for your induction motor, this is DC motor, that is why no need to consider the power factor. So, for your induction motor torque equation, we can write directly like pi flux also available here. What is Ia? Is armature current. Here rotor is rotating, that is why I2. Here we need to consider power factor, that is why cos phi 2. That is, now we can write simply like this, but we need to derive also what is I2 and what is cos phi 2, because during rotation our frequency Fr running time is equal to slip time supply frequency. So, if the supply frequency changes, our during running condition our reactance, that is rotor reactance, also changes like this, and our if reactance changes, our Z2, that is impedance, also will get affected, R2 square plus Sx to the whole square, and our current also will get affected, because I2 under running condition is equal to E2 under running condition, that is EMF induced under running condition, divided by this Z2R. That means our voltage also affected because of the change in flux, though this is also S into E2. That is why our I2 under running condition is equal to S into E2 divided by Z2R. Okay, now this is our this is running condition, that is why put the subdivision R. Now, our I2R is found like this. What is my cos phi 2R during running condition? That is cos phi 2R nothing, cos phi is nothing but R by Z. You know the familiar formula, R by Z. Here R2 by Z2R, R2 by Z2R, and the phi is directly proportional to our rotor EMF. Now, substitute all the equation in our torque is nothing but phi, instead of phi we can substitute E2, and instead of I2R we can substitute S into E2 divided by R2 square plus Sx to the whole square, that is square root. into R2 divided by R2 square plus Sx to the whole square. Now, we can simplify the equation S into E2 square R2 divided by R2 square plus Sx to the whole square. That is the torque equation. The torque equation is nothing but T is equal to S into E2 square R2 divided by R2 square plus Sx to the whole square. That is our torque equation. So, now the torque equation which is having slip, rotor EMF, rotor resistance and also rotor reactance. Now, when we will reach the maximum torque? Maximum torque, when we will reach the maximum torque? So, the derive the condition for maximum torque, differentiate this torque equation with respect to slip and equating to 0. Differentiate the torque equation with respect to slip equating to 0, that is our we can find the getting the result R2 is equal to Sx2, that is the motor reaches the maximum torque, our rotor resistance is equal to S into X2. That means, during loading, if we apply the load gradually, our slip will change. Why? Our slip, what is our slip? Slip is nothing but Ns minus N divided by Ns. Ns is constant. What is N? Is rotor speed. If the load is applied, our rotor speed will going to reduce. Proportionately, our slip will get affected. That is why S into X2 will change. So, the Sx2 will increases from our no load. At no load, the synchronous speed is nearly equal to synchronous speed. After applying more loads, our speed is gradually reduced, our slip is increases. That means, our Sx2 will increases at certain period, the condition is reaches R2 is equal to Sx2, that is the condition for maximum torque. If you apply the load after this instant, instead of increasing the torque, our torque is going to decrease. So, our current also decrease, the motor is going to stop. So, we can, there is a maximum point, the stalling torque. So, we can apply the load up to this instant, that is R2 is equal to Sx2, that is a condition for maximum torque. Now, up till now, what we are discussed today, what is 3-phase induction motor? What is 3-phase induction motor? According to the principle, which is the principle is mutual induction, that is why it is called induction motor. Also, we have studied about construction. We have the two types of construction, squirrel cage rotor and slip ring rotor. And why it is rotating? If the supply is given to the stator, one torque will develop, the torque only responsible to rotate our rotor. And finally, we have derived the torque equation. This much torque will develop for your 3-phase induction motor. Also finally, we have derived the condition for maximum torque. We can apply the load maximum point this much, R2 is equal to Sx. So, today what we discussed up till now? Up till now we are discussing about what is the need of 3-phase induction motor and what is the speciality of 3-phase induction motor. Now, our 3-phase induction motor is used wide variety of applications. 99% of application we are using 3-phase induction motor. That is why we are mainly concentrating this construction. And first we have studied our construction, how to construct our stator and how to construct our rotor. The rotor we have two types, the squirrel cage rotor and slip ring rotor. So, the squirrel cage rotor we cannot add any external resistance. For your slip ring rotor we can add external resistance, because through the slip rings some resistance is rheostat is added. We can add the rheostat, we can change our torque, because the torque equation which is having rotor resistance, the torque is directly proportional to our rotor resistance. That is why if we change our rotor resistance, we can change our torque, proportionately our performance also affected, but which is not possible for your squirrel cage induction motor. And also the next we were discussed why it is starting, why does our rotor will rotate. The 3-phase supply is given to the stator, which is responsible for the rotation, that is rotating magnetic field. The 3-phase supply is given which produces rotating magnetic field. For your single phase induction motor and synchronous motor is not having self starting, because not single phase induction motor not able to produce rotating magnetic field, because only one phase is there. So, to produce starting we will change our motor at starting to the 2-phase motor to make self starting, but here it is able to self start because it produce rotating magnetic field. And also one more point we discussed, our rotor always rotate less than synchronous speed. If our rotor catches the synchronous speed, what will happen? Not possible, the flux cut by the conductor is not happen, no EMF induced for your rotor conductors, not possible to production of the current. That is why not possible for your EMF and not possible for your rotation. That is why our rotor always rotate less than synchronous speed. So, the force developed is not possible if the rotor and stator flux rotate at the same speed. That is why our rotor always rotate less than synchronous speed. So, before starting the EMF induced, the frequency of the EMF induced equal to supply frequency. After the rotation, the frequency of the induced EMF is equal to slip times supply frequency. Using this concept, I am going to derive, we have derived our torque equation. So, finally we have derived our torque equation is equal to S E2 square R2 divided by R2 square plus Sx to the whole square. And also finally we have derived the condition for maximum torque, how much load can applied. So, if the load is applied, our speed will reduce, our slip also increases, our Sx2 increases. If Sx2 is equal to R2, that is the condition reached maximum torque. If you increase the load after this instant, the machine eventually stops. That is all. Thank you.